In this video, I'd like to discuss how mathematical expressions can be built and manipulated algebraically with, I think, some rather remarkable and surprising outcomes. I'll begin by relating a childhood experience that really stayed in my long-term memory and stimulated my interest in mathematics. Some people have bad or unpleasant experiences in early childhood that put them off mathematics. I was lucky and had a very fine teacher. One morning, he came into the classroom and said, "I want you all to think of a number between 1 and 10. It's your own secret number. Don't tell me or your friends. I want you to double it. Add 4. Halve what you see in your head. Remember your secret number. Don't tell anyone. Take it away. You are now thinking of the number 2. We were all indeed thinking of the number 2. This was quite astonishing to a child, and what was even more remarkable was that the teacher was able to explain carefully why we were all thinking of the number 2. Call this secret unknown quantity x, build up an algebraic expression that corresponds to the instructions, and see that it simplifies in every case to the number 2. It was, for me, quite amazing and powerful, my first experience of mathematical proof. I'd like to show you something surprising about some common everyday objects. Sheets of paper, in fact, in the A series. Here's A4. This is A5, half as big. A6, half as big again. And A7, half as big yet again. 2 A5s make an A4. 2 A6s make an A5, and so on. These pages are all rectangles. You can have thin rectangles, thick rectangles, rectangles with perfect symmetry known as squares. But notice that all of those sheets of paper in the A series form similar rectangles, by which we mean they have the same proportions. How can we prove that? Well, we can draw lines along the diagonals of each of them. If the diagonals all line up, then the rectangles are similar. See how all the diagonals line up? We can continue creating smaller and smaller similar rectangles forever just by dividing the sheets in half. Now, the diagonal lines of rectangles have a slope, and slopes are really important in calculus. So what we'll do now is try to understand this particular slope associated with the A series of sheets of paper. The slope is just the ratio of the side lengths. Here we have a diagram of an A4 sheet of paper divided exactly in half, so the two halves represent A5 sheets of paper. Call the longer side length B and the shorter side length A. So the shorter side length of the A5 half is B on 2, and its longer side length is A. Let X denote the ratio of the longer side length to the shorter side length. So for the A4 sheet, this is B on A, and for the A5 sheet, this is A over B on 2. Multiply top and bottom by 2, then divide top and bottom by A, and we get 2 divided by X. Thus, X is equal to 2 over X, so X squared is equal to 2. So X must be the square root of 2. Just using algebraic manipulation, we discover that for the A series of paper, the ratio of the longer side to the shorter side is the square root of 2. Now, from your calculator, you'll see that the square root of 2 has this decimal expansion, and it goes on forever. There's no repeating pattern of digits because the square root of 2 is irrational, something we discussed last time. How does the calculator know that this is the correct way to start the decimal expansion? I'll show you a surprising consequence of algebraic manipulation. First, remove the 1 at the front by subtracting 1 from the square root of 2, and we get this mysterious decimal expansion after the decimal point. Now, in mathematics, it's very important for all sorts of reasons to be able to reciprocate or invert numbers. Just for fun, let's play around with the reciprocal of root 2 minus 1. Who knows where it may lead? We get this awkward-looking fraction. Any mixture of symbols involving the square root sign is called a surd expression. How might we simplify it? There's a technique explained in the notes called rationalizing the denominator. I won't go into the details here, but in this case it involves multiplying the top and the bottom by root 2 plus 1. When we do this, the numerator just becomes 1 times root 2 plus 1, which is root 2 plus 1, and the denominator becomes root 2 minus 1 times root 2 plus 1, which becomes root 2 squared minus 1 squared. This comes from something called the difference of two squares formula. A squared minus b squared is a minus b times a plus b, which we apply here with a equal to root 2 and b equal to 1. And so, because of this neat trick, the fraction simplifies in a couple of steps to root 2 plus 1. Thus we have shown that the reciprocal of root 2 minus 1 is root 2 plus 1. Reciprocating again, that is turning the fraction over, we get root 2 minus 1 is 1 over root 2 plus 1. Now there are more neat tricks. We can subtract 1 and add 1 in the denominator without altering the overall value of the expression. And then this becomes 1 over root 2 minus 1 plus 2. Now in mathematics and computer science, you almost always discover something interesting or useful if you can set up some kind of self-reference or recursion. We have that here. Now what do I mean? Well, put y equal to root 2 minus 1. So y equals 1 over y plus 2. And it's convenient to swap the 2 and the y around. This doesn't alter the value of the expression. And we get y equals 1 over 2 plus y. Now why should we get excited by this? I remember when I was very young having porridge for breakfast, and the oats came out of a packet with a picture of a man holding a packet, with a picture of a man holding a packet, with a picture of a man holding a packet, and so on forever. It was intriguing, mind-boggling, that infinity could sneak its way into the kitchen. And we have that here. Y is our packet of oats with this self-referential property. We can feed y into itself, again, and again, and again and again, going on forever, creating what is called a continued fraction expansion. Remember, y equals root 2 minus 1, so here's its continued fraction expansion, going on forever. Of course, we can't compute with infinite expressions, but we can approximate them. What we do is truncate the expression somewhere, say here, and equals becomes approximately equals. And then evaluate this fraction on the right-hand side inside out. We get 5 on 2, which becomes 2 on 5, which unravels in a few steps to become 29 on 70. Thus we have that root 2 minus 1 is approximately equal to 29 on 70, so root 2 is approximately 1 plus 29 on 70, which equals 99 on 70. We've just played with simple numbers and come up with this approximation. So how good is it? If you square 99 on 70, you get 9,801 divided by 4,900, which is almost 9,800 on 4,900, and that's exactly equal to 2. The difference here is 1/4,900th. So close. If you start dividing 70 into 99, you get a recurring decimal expansion after several steps with repeating digits ad infinitum. Here's the decimal expansion of root 2 again. Notice that these decimal expansions agree up to the first 4 digits past the decimal point. Now we just took a few layers of the continued fraction, and just in a couple of minutes we produced a rational number approximation whose expansion gives the first 4 digits of root 2 after the decimal point. Now before mathematicians had calculators, this is how they would get such amazingly accurate approximations of numbers. They'd use some kind of clever algebraic manipulation to get an approximation involving fractions, which in turn involve simple counting numbers. And then it becomes straightforward, though possibly tedious, to write out the decimal expansion, which eventually repeats, being a recurring decimal. Just for fun, you could go back to that truncated continued fraction, add some more terms, and get an even more accurate approximation of the square root of 2. We've covered a lot of ground in a few minutes, including developing some techniques of algebraic manipulation, looking at surd expressions involving square roots, including a rather surprising example of reciprocation leading to a recursive formula, and a novel method of approximation using a continued fraction. There's more detail in the notes, and I'd like you to read and digest them. When you're ready, please have a go at the exercises, which should give you a thorough workout with manipulating fractions in all sorts of combinations, including symbols and numbers, and some practice with the technique of rationalizing the denominator of a fractional surd expression. Thank you very much for watching, and I look forward to seeing you again soon.